All right, once again, you guys are welcome to today's section. And today we'll be talking about key points on the dynamics of the solar environment. Now, I wanted to just share this with the group leaders, like I said earlier, but because of the urgency of now, I have to share it with everybody, which again is an advantage. In fact, this is not actually part of the bureau. This is something we prepared for what we call the Brian Space Academy. So we are giving you guys what we did not, I mean, more than we promised to you guys. So once again, I'm Amadi Brians Chinonso, and I'm the program director of Brian Space Associates and one of the organizing committee member of BREP 2026, alongside Roberto from Brazil and also Ipsita from India. So today we'll be talking about the sun, like I said. And what I wanted to do, like I have said, was to talk to the leaders about the importance of, of what we did in the last session, about uh, the impact the sun can have. So we'll be talking more about geomagnetic storms. We'll define all of this to you guys. Some of you already know about it, but for those who don't, we'll also talk about it. And why do we need to talk about the sun? That's the most important thing. When you talk about space weather, everybody who talks about space weather, some way, somehow looks back to the sun. So why do we look back to the sun? It is simple. Because in our project, what we'll be talking about will be the ionosphere, and we'll be talking about storms in the ionosphere. And these storms are driven by magnetic field in the solar winds. Because what the sun is actually giving out is not just particles, it's also giving out magnetic field. And this magnetic field can impact our geomagnetic system or our geospace. So the source of this magnetic field within the solar wind is the sun, the dynamics of the sun. And that is why we all walk back to the sun each time we try to talk about space weather. So the space weather we'll talk about in the ionosphere is caused by magnetic field in the solar wind, and the solar wind is varied by the dynamics in the sun. So the sun drives all the variations we see in the solar wind and affects our near-Earth space environment. So in your project, you'll be talking about the different impact of one storm or the other. But then, what is the cause of that storm? The magnetic field contained within the solar wind driven by the sun. And this is what we wanted the group leaders to understand. So we'll be going through again some of the components of the sun, the dynamics of the sun that, drive all these variations we are talking about. First, once again, I would want to add some emphasis on what the sun, what the sun is really. Of course, we all know the sun is a star, but then why is it called a G2V star? Now, there are different classes of stars, like many of you, some of you, like I saw in your CV, are astronomers. So you already know we have classes of star. We have the A, the F, the G, the M, O, and so on. Now, why is the sun called the G star? The sun is called the G star because its surface temperature lies between 5,000 to 6,000 Kelvin. But why is it called G2? Why do we add that 2 to the G? It's called, okay, it belongs to the G class. Why the 2? The 2 is because it is the second class or the second subclass in G class. So in G class, we have the first class, we have the second class, and so on. Our star, the sun, belongs to the second class. And then we also have the V there. The V simply tells us the phase in the evolution of our star. Of course, we all know we have from the red giant, you have the protostar, you have the main phase, and so on. We now know that the sun is in the main phase of its evolution, and it's just 4.6 billion years old, and we are told it has 7 billion more years to live. So for those of you who will be here by that time, maybe the sun may have, of course, changed its phase, its color, and so on. So presently we call the star a main sequence star, and that means we denote it by V. And that is the source of that G2V classification of the sun. There is one last thing I want you guys to take note of. We all know the sun is we call the sun a yellow star, but then scientists also say the sun gives out only white light. So why is it called a yellow star? Most of you must be aware about spectrums. And in the spectrum, we have different colors, different wavelengths. So the the sorry, all right. So the peak wavelength of all the spectrum, that's the spectrum with the peak when it comes to the spectrum of the sun, is yellow. And because of that, the sun is called a yellow star. Not because we see it as yellow from the surface of the earth, no, but because of the intensity of the yellow spectrum within the spectrum of the radiation coming from the sun. That's why we also call the sun a yellow star. So it's classed as yellow dwarf despite being white because the yellow wavelength dominates its spectrum. So that's a very important point for most of you to note, especially those who will be carrying out the project. And then we have some common features of the sun. Many of you have heard about this before now. You know the mass of the sun, of course, 2 by 10 raised by 30 kilogram. That means you can have about 330,000 Earths, compressed within the sun. So the mass of the sun is really massive, and that's why we call it the center of our solar system, right? And that's why it's able to hold all the planets in their position, orbiting around it, because of its mass. So, for those of you who know about the law of gravity, that's a gravitational pull, you should understand uh, why the sun is able to hold every other planet around itself. One of those reasons is its mass. It's very massive, right? And then we also have the radius of the sun to be about 700,000 kilometers, and the surface temperature of the sun. Please note there is a difference between the surface temperature and the temperature of the core. These are two different things. And also, when we say surface temperature, we are not talking about the temperature of the corona, which is outer part. We're talking about the temperature of the surface of the sun, that's around just below the photosphere, which is about 5,700 Kelvin. And then at the core, temperature of the core is about 15 million Kelvin. Some of you already know about that. So I wouldn't want to talk about this, but there is some about other components. But there is something very important I want you to know about. That's how energy is produced in the sun. You already know that it's from nuclear fusion, right? The fusion of hydrogen into helium, and you have a byproduct, which is the radiation and the heat we receive here on Earth. So these are some common facts about the sun. Yeah, I've talked about this. So you have the solar strata. I've talked about some of this part. The solar strata have to do with the layers, of course, of the sun. We all know from the inside we have the core. We also have the radiative zone, and then the convective zone, the photosphere, the chromosphere, and then the corona, which is the outermost part, right? There is something I want you guys to take note of here. Some of you may have heard about it, but it has to do with the variation in temperature as you move from the center of the air of the sun to the outermost part. At the center, you can see a very high temperature, 15 million Kelvin. And then when you get to the photosphere, which is the surface, you have about 6,000 Kelvin. But then beyond the surface, you see the temperature increasing again from about 4,000 Kelvin to 8,000 Kelvin. And when you move further up away from the sun towards the corona, you have up to 2 million Kelvin. Why do we have this mysterious change in temperature of the sun as you move away from the center of the sun? So I would want to use a kind of fireside analogy. You have a little boy right here. So this little boy, when he's close to the fire, of course, we expect the heat to be more. And in the second column, you can see the boy moved away a bit away from the sun. We expect that the heat that boy is receiving should be reduced. And the third column, in the third column, we expect that as the boy moves away from that fire, the heat he's receiving from that fire should decline significantly. I believe you guys should agree with me. But this is not what we see in the sun. In the sun, you have an increase in the temperature at a certain point as you move away from the sun. For me, this is a mystery, and for so many scientists, also a mystery. So, up to today, we're trying to find out what is the cause of this variation, this sudden or mysterious variation in temperature of the sun. One of the drivers of this variation is what we call nanoflares. That's very small flakes. And then you also have Alvin waves. What are nanoflares? Nanoflares are very small concentration of energy we have in the sun, and it's able to convey energy from the internal part of the sun to the outermost part of the sun. So what you see here is an example of a nanoflare. This is not really a nanoflare. They call this a microflare. But then the smaller component or a smaller part of this is what we call the nanoflare. So it's very difficult to observe the nanoflare, of course, because of the overall brightness of the sun. So they are usually masked within the sun. And you also have another cause, which we call the Alfvén waves. Now, these Alfvén waves are simply oscillations due to vibrations of ions and plasma within the sun. Some scientists are of the opinion that these variations, these oscillations, causes the variation we see, the sudden increase we see as you move from the photosphere to the corona. So these are 2 points I would want you guys to take note of. For those of you who will be going into heliophysics, know these two main causes. I actually learned this also in graduate school. So, and we're told about why this aspect is important, because the belief is that some of us within the class may go on to study, heliophysics, and it's important for us to know that this is an unsolved problem. But for now, we just know that the cause of some suggestions about the cause of that mysterious increase are nanoflares and also Alfvén waves. Then we also have very interesting occurrence or observations in the sun, and it has to do with flips in the magnetic poles, and also we have the circles, the variation in the solar circle. Now, we know that the magnetic field of the sun flips with time every 11 years, roughly every 11 years. So as you can see from this plot, the polar field is high here, but with time it decreases to about to negative, from it decreases down to 0 and then to negative values, and then it starts increasing again, and then it reverses with time. So this 11-year period is actually synonymous to the number of sunspots observed. I'll tell you what those sunspots is. But then what we call this variation, this increase and decrease, is a solar cycle. The 2 points I want you guys to take very strong note of is the flipping of the magnetic field every 11 years. It actually flips, and it's important that you know about these flips. So why do you need to know about this flip is something that is also very important for your project. Assuming you're carrying out this project for a period, you need to understand if that period it's a high solar activity period, or if it is a low solar activity period. And how do you know if it is a high solar activity period or a low solar activity period? During a high solar activity period, we observe this increase in the polar field. And during a low solar activity period, you observe this decline or this reverse in the polar field. So these are descriptions that are important while you're writing maybe papers for a geomagnetic storm. And the cycle of low and high solar activity is known as a solar cycle. And you can see this in this plot here. So you can see this decrease at this point, and then an increase, the decrease, and increase, and so on. That increase and decrease simply tells you the number of sunspots observed on the surface of the sun. What are these sunspots? I'll tell you what they are. But for now, understand that we have this decrease in the number of sunspots and increase in the number of sunspots. That period of increase and decrease is also called a solar cycle, and it coincides with the reverse in polar field we observed on the sun. So what are sunspots? Like I've said, it is the number of sunspots that actually determines a solar cycle. One solar cycle is made up of a decrease and an increase in the number of sunspots. So what are these sunspots? When you take a very close look at the photosphere using certain kind of instrument, for example, SDO and maybe SDO and SOHO, you observe at some point very dark spots using this instrument. Sorry, excuse me. Let me mute this person. Sorry, please, everybody should mute themselves. Thank you. Oh, there. Sorry, let me mute this person. Oh. Can I mute this person? All right, sorry about that. Please, it's important that you all mute yourself so that we don't distract each other, right? And if you have other activities you're involved in, you can exit the meeting. All right, I hope everybody can see my screen. So as I was saying, we have sunspots, the very dark spot you see on the photos. And each sunspot is made up of a very, very dark interior, which we call the umbra. And then we have the outermost part, a, a relatively dark but not very dark outermost part, which we call the penumbra. So this makes up the sunspot. And what is the driver of sunspot? The drivers of sunspot are actually closed magnetic field lines. Now, I want you guys to understand, when you read most books, you're told that the sun is a ball of hot plasma or hot particles and so on. In my mind, I prefer to say that the sun is actually a ball of magnetic field lines. And the dynamics of these magnetic field lines actually, causes the variations and all the phenomena we observed in the sun. For example, in the case of sunspot, what we know or what scientists know today is that the sunspot is caused as a result of the closing, the entanglement of magnetic field lines. That entanglement causes some kind of it obstructs the flow of heat. And that obstruction thereby causes that surface to be cold compared to relative areas. So when you measure the temperature of a sunspot compared to the areas around the sunspot, the sunspot is cool. The temperature is lower. When I mean cool, I don't mean cool as in cool. I mean it's relatively uh, it's a relatively low temperature area. And why do we have that low temperature area? It's because the entangled magnetic field obstructs heat from reaching those regions. And that is why we have that dark spot there. And it's actually located on the photosphere. So for those of you who will be leading this project, I would want you to connect all your projects to what you can see on the surface of the sun for a given storm. For example, if you're studying the storm of a certain day, it's important you go and check what the sun is doing on that day. Take a look at the sunspot. Can you see sunspot? How many of them can you see? And so on and so forth. So of course you'll be shown where to get this data or these images, and then you have a look at what the sun or how the sun is for that given storm. So before you start writing about what happened in the ionosphere, you should be able to understand what happened on the sun and the different structures you're going to see on the sun. So we'll be talking about more of them subsequently. So this sunspot usually occur around the equator. And for those of you who were here in the last session, you must have seen this, right? You must have seen this butterfly diagram. This butterfly diagram is simply the plot of the location of sunspot against time. There are two things I want you to observe. The sunspot occur very close to the equator. That's one. And then secondly, you observe that as we move towards the end of a solar cycle, the sunspot tends to drift closer to the equator. And that is what that butterfly diagram is saying to us. Take a look at this circle here. So at the beginning of the circle, you can see that the sunspots are located at around 30° north and 30° south of the equator. But with time, observe that with time, the sunspots are located closer to the equator, right? And that gives us the butterfly diagram. So it's just for knowledge. You may not need this knowledge for the project, but for those of you who will be going to maybe graduate school for PhD and so on, or maybe you want to become a heliophysicist, it's important for you to have these basic understandings about the occurrence of sunspots. And again, I have already shown you this solar cycle. This is from 1880 to 2010. So you can see the increase in the number of sunspots with time. So the number of sunspots increases from the beginning of a solar cycle to the middle and then decreases again with time. And that gives us a full solar cycle. So if you ask what an 11-year solar cycle is, you should know that it has to do with the increase and decrease in the number of sunspots observed on the surface of the sun. So that is for sunspot. We have another interesting structure we call the prominences. When you take a look at different images of the sun, you see these glowing filamentous, uh, uh, twisted magnetic field lines. They are usually glowing, they are usually filamentous, and usually associated in some cases with massive ejections of particles from the surface of the sun or from the corona of the sun per se. So this is an example of a prominence. Some of you said you'd like to see images of some of these things. I heard this from the feedback you guys gave, and that's why I had to, add these images to ensure that you guys have a picture of what these prominences are. So this is an ejection, but this is called a prominence because of its filamentous nature. There are other ejections that you see. You may think they are. In this case, you can see the filamentous nature of the ejection. You can also see that it is glowing, though in some cases it's also associated with what we call solar flares, which some of you already know about now from our session in the last lecture. So why are we saying this? You should be able to describe if you saw a prominence for a given storm. So when you're talking about the ionosphere, you should be able to tell us, okay, it seems this occurred because a prominence occurred, and you could see it to the occurrence or observance of a prominence from the sun. And then we also have what we call coronal mass ejections. Some of you already know about this too. Now, these coronal mass ejections, as the name implies, they are massive. They are ejections from the sun, of course, ejection of particles and magnetic fields, and they are massive. They are usually large in billions of tons of kilograms. And as you can see, so let me go back so you can see what these ejections are. So these massive ejections actually are sources of most of the solar storms we observe on Earth. So this is one of the most important concepts you guys should have, or most important information you should know at the end of today. So these coronal mass ejections are responsible for most of the solar storms or geomagnetic storms we observe on Earth. So this is what they look like, as you can see. So I believe you guys can see that ejection from the sun. And that is it. So it's massive and it's large. And we have another one called a solar flare. This is another kind of ejection. But in this case, it's a very giant explosion of light and energy as well as particles. So as you can see, so take a look at that. So what you can see how bright it is compared to other parts of the sun. Despite the sun being bright, there is a part of the sun that is brighter. You know, whenever you have the solar flares, you have them to be brighter than other parts of the sun. So that very bright aspect you have on the sun is what we call a solar flare. So they are not like, they are not ejections per se. They are ejections in the sense that they eject light, they eject light energy, they eject particles, but they are not massive ejection of particles like we see in a coronal mass ejection. So these are similar but very different ejections we observe from the sun. And these solar flares also causes ionospheric storms. They are source of ionospheric storms and can also cause geomagnetic storm, like the May 24th geomagnetic storm. What we saw on the sun was mostly solar flares. We also had coronal mass ejections. So at the end of this lecture, you guys should be able to distinguish between coronal mass ejections and solar flares. So see how very bright solar flares are. I believe you should be able to distinguish a solar flare and a coronal mass ejection. So very, very bright. Very, very bright. All right, so let's characterize the coronal mass ejections that we have. So we have classification of coronal mass ejections based on speed. We also have classification based on other factors we'll talk about. But based on speed, we have slow and fast uh, coronal mass ejections. So the slow coronal mass ejections have speed of about 300 kilometer per second. That's less than 300 kilometer per second. While the very fast ones have speed greater than 300 kilometers per second. So when describing the solar condition for a given day, you should be able to describe if the coronal mass ejection is a fast one or a slow one. This is why I wanted to have this conversation with the group leaders. So now that everybody is involved, you should be able to give this description, when describing, the geomagnetic condition of a given day. So is the coronal mass ejection causing that geomagnetic storm a slow coronal mass ejection or a fast coronal mass ejection. Now, I won't be using the term coronal mass ejections anymore. I'll be using the term CMEs for abbreviation. As an abbreviation, I mean. So you should be able to tell if the coronal mass ejections are slow or fast. So is it a slow CME or was it a fast CME? You should be able to distinguish between these two kinds of CMEs. And then we also have classification based on intensity. We have weak, strong, and moderate intensity, intense as CMEs. So when we say weak, we mean CMEs that have uh, that emit associated with ejections of about less than 0.1 billion tons of particles. That's in kilogram, right? And when we talk about strong CMEs, we're talking about those that have more than 1 billion tons in the mass of the particles they eject. Then we also have those from 0.1 billion tons to 1 billion tons in kilograms of the particles they eject. Those are called moderate CMEs. So you should be able to tell if the geomagnetic storm was caused by a weak CME, a moderate CME, or a strong CME. These are terms you should be able to use in describing in your papers, in your articles, in your journals, and so on. And then we also have by halo or by direction, I mean. Is it halo or partial? When we say halo, we mean, you know, uh, we use coronagraph to observe the environment, the atmosphere of the sun. So if the CME is coming directly in the directly towards the coronagraph, it means that's a halo CME, and it means it's coming towards Earth. But if it is partial, if, for example, we are only seeing part of the CME within the coronagraph, that means it's likely not to hit Earth. It's likely not to cause any geomagnetic storm, likely, but that's not for sure. So based on direction, it's either coming in direction of Earth or away from Earth. So you should be able to describe if the CME was maybe originally not coming towards Earth, but finally diverged in direction and then came towards Earth. You should be able to give all of these descriptions in your writings, in your articles, in your projects. And then we also have characterization of CMEs by association. Are they associated by flares or are they associated by prominences? Now, those associated by prominence are usually called gradual CMEs, and those associated with solar flares are called impulsive CMEs. There are some CMEs that are associated with solar flares. Those CMEs are called impulsive CMEs. So you should be able to also describe these structures or these dynamics of the CMEs you observe on the image of the sun. That's SDO or SOHO images. And then we also have classes of flares. That's the solar flares. We have the X flare. That's the most impactful one. The X flare, for example, what you're seeing on your screen is an X flare, the brightest class. We classify solar flares based on intensity. And X-class solar flares are the most intense. They are the biggest, the most impactful. So whenever you have S-class solar flares, like we have, I think, in 10th May 2024, that's a very impactful solar flare. So assuming you're working for maybe for sorry, excuse me. Assuming you're working for, let's say, an observatory and you're able to see some of these images before other scientists, you should be able to tell, what class, how intense that solar flare is. So we have the S class. We also have the M class. So what you're seeing on your screen right now is an M class solar flare. You can see it's not as bright as the S class solar flare, right? So those are medium. And we also have the C class solar flare. Now I want you to know something. The S class is more intense than the M class by a factor of 10. The M class is more intense by the C class also by a factor of 10. And the C class is more intense by the B class, also by a factor of 10. And the B class is more intense than the A class by the factor, again, by a factor of 10. So these are some of the points you should know. So we have the S class, the M class, C class, and the B class, as well as the A class. So S class, M class, C class, and then B and A class are very rare. They are very small, sometimes not seen. They are very small flares. For me, I prefer to, I mean, some people don't classify them as microflares, but sometimes I prefer to call them microflares because they are the smallest and sometimes not observable. And then we have very, very important structure we see in the sun. Uh, okay, I think this is time for us to take maybe a short break. But then before we go for that break, I want you guys to know about the corona hole, and then we'll also talk about the corona loop. Some people, for example, personally, I was confusing these two nomenclature to be the same before I went to for graduate school. But after graduate school, I realized they are very different structures. So I'll allow you guys go for maybe a 5 minutes break, and then when we come back, we'll continue. Is that okay? All right. So we'll go for a 5 minutes break, and then we'll continue in 5 minutes time. All right, I'm back. So can we continue? Nice. Uh, yeah, I just removed somebody from this meeting. So maybe, so please, we wouldn't want all those distractions. Try as much as you can to mute your microphone and video whenever you're in the meeting. And if you have other things you're doing, it will be nice if you just focus on whatever you're doing. And if you want to be here, it will be nice if you focus on this, right? So I had to remove him because it has happened severally, not just once. All right. All right, so let's continue our conversation. I hope everybody can see my screen the ways. I was trying to confirm that. Okay, so I was talking about coronal holes and lobes. I I believe everybody now know about the strata of the sun, the layers of the sun, and you know the part we call the corona. So uh, whenever we have any structure associated with the corona, we usually call them coronal. So coronal mass ejections, coronal holes, coronal loops, and so on. So what are these coronal mass ejections? You already know them. And then let's talk about coronal holes. So when you take a look at the image on your screen, you see this huge hole here. You see another one here, and you see another one here. These depleted regions are called coronal holes. And they are regions of magnetic field lines that have broken up, that are open, that are disconnected. So when magnetic field lines disconnect, break up apart, you know, in high school you were told magnetic field lines, of course, you can't split magnets into two. But when you go a bit further, you realize that magnetic field lines can connect and disconnect, connect and reconnect. So On the sun, when we have this disconnection, they become open. And the implication of this openness of of magnetic field lines is that the particles on these magnetic field lines become free to flow out. And when they get free to flow out, that region from which they are flowing out gets depleted, gets, let's say, empty, becomes empty, right? That's why you're seeing this empty region here. And that's why you're seeing these empty regions you're seeing here. And that's the same reason we have an empty region here. It's not really empty, it's relatively empty compared to other regions. So you can see other regions are filled, but these regions are open. So for that reason, we call them holes. And this occurs in the coronal. And because they occur in the coronal, they are called coronal holes. So take note of this. They are formed as a result of open magnetic field lines. And one consequence of having these open magnetic field lines is that you have particles breaking away, leaving the surface of the corona of the sun massively. And the implication of that is that they increase the speed, they drive the speed of solar wind. That's how we get what we call fast solar winds. So I'm just trying to rotate the image so you see uh, the coronal mass ejections from different perspectives. So those are coronal holes, and they are formed as a result of open magnetic field lines, like I said, and they drive fast solar winds. In other words, they increase the speed of solar winds emanating from the corona of the sun. The images are heavy, that's why it's slow to rotate. So you can see this hole that looked very small from the other side. You can see how big and huge it is, right? So there, and you can see the coronal hole that was here, it's no longer visible to you. So I wanted you to see how huge that coronal hole is. It was looking small from a different perspective, but you can see how huge it really is. So these are coronal holes, and so let's talk about coronal loops. So we have these loops also formed by magnetic field lines, but in this case, they are different. While coronal holes are formed as a result of open magnetic field lines, coronal loops are suspended particles from the surface of the sun as a result of closed magnetic field lines. You can see that you can see the magnetic field lines and the particles, on those magnetic field lines. You can see that it is not broken. You can see the loop. So this loop is not really a loop of particles, but a loop of magnetic field lines, formed on the surface of the sun, on the corona, I mean, the atmosphere of the sun per se. So these are clearly two different phenomena, very different from coronal loops, very different from prominences. They are not even coronal mass ejections, though can be associated with coronal mass ejections. Neither are they solar flares. Even though you're seeing this brightness, they can be associated with solar flares, but they are not solar flares. Coronal lobes are simply closed magnetic field lines, and they are usually rooted in sunspots. Now, I want you to know this. Coronal mass ejections are actually associated with sunspots. So whenever you have sunspot, it's likely that you have coronal mass ejections. And these coronal mass ejections are also sometimes associated with coronal lobes. So they all have, some kind of associations. So it's now up to you to look at the image of the sun and be able to distinguish all of these structures, as much as you can. And then we have the sun's wind, which you all know as solar wind. Many of you know about the solar wind already. But before 1958, nobody knew about them. But in 1958, Eugene Parker, a scientist, predicted that there must be this wind of particles coming from the sun because he was trying to balance all the forces, all the masses, from his calculations, from his computations. And there was something missing from all of his computations. And he said, the okay, let me give you guys an overview of how he came about that. There is this belief that the gravitational pull of the sun is able to hold all of the particles in place. But considering the hotness of the particles, Eugene Parker said it is not possible, for for Earth's gravitational, for the sun's gravitational force to hold all of these particles in space within that ball, within that sphere we know as the sun. It's not just possible from his calculations. He then predicted that because of the hotness, because of how energetic these particles are, that there must be particles leaving the surface of the sun, leaving the atmosphere of the sun. And he then predicted that very likely we are going to have a wind of particles coming from the sun because the gravitational pull of the sun cannot hold them. They are too energetic to be held. And in 1959, a satellite called Luna 1 was able to confirm that truly there are particles coming from the sun. There is this wind of particles coming from the sun. And with that, the prediction of Eugene Parker in 1958 became a reality. And that's why we are talking about the solar wind today. Before 1958, we never knew about the solar wind. But from 1958, 1959, we now confirm that we have wind of particles from the sun, and we call them solar winds. They have speeds of about 400 kilometers per second, and they are mostly coming from the atmosphere of the sun, which we know the outermost part of the sun, which we call the corona. I believe everybody now know about the corona. So that's the solar wind, as you can see from the sun. And then one last thing I want you guys to know about is in 2018, there was an observatory or a probe launched into orbiter, into space, I mean, and that orbiter was called Parker Solar Probe in honor of Eugene Parker, right? Who predicted the who predicted the existence of a wind of particles from the sun. That's solar wind. So and this probe has been able to touch the sun. Now, some of you may not have known about this before now. Some of you may not believe that anything can touch the sun. A friend and I already had an argument where we talked about if anything can go close to the sun. And for me, I told him we've already had stuff that already touched the sun. And I was talking about the Parker Solar Probe. He said nothing on Earth can actually go close to the sun. And I showed this to him, right? So it's a very interesting probe to study. For those of you who will be more interested, you can go study about the Parker Solar Probe. And you try to understand, despite the hotness of the sun, despite the temperature of the surface of the sun, despite the temperature of the corona, how is Parker Solar Probe able to get close to the sun? In fact, just in March, that's about last week, yeah, it it went the closest it had ever gone to the sun. So how is it able to do this? It's able to do it using some kind of, cooling devices, water and other cooling devices. It also have the carbon composite temperature uh, cooling system. So this object, this probe has been able to touch the sun, and it's been able to give us a whole lot of information, more information about the solar wind. And I want some of you who will be interested in going into heliophysics to consider using the data from Parker Solar Probe. I can't recall if it is public now, but you can check if it is public. I think it should be. There should be public data from that probe. So we've been able to touch the sun. Parker, Parker Solar Probe has been able to touch the sun, and it went the closest it has ever gone to the sun on the 11th of March of 2026, and it's able to survive as a result of some kind of carbon composite materials embedded in the probe. So it's not really important for our project, but I just felt for those of you who will be interested to go into heliophysics, you may want to, consider using data from Parker Solar Probe. And this mission is actually between NASA's and John Hopkins Applied Physics Lab. So if you want to know more, you can read about this. And then one last thing, you guys should be able to identify solar features. That's the essence of this session. You should be able to identify solar features we have on the sun, on any surface of the sun, on any image you can see of the sun. So you should be able to identify the coronal mass ejections. You should be able to identify the solar flares. You should be able to identify the coronal holes. You should be able to identify, you know, uh, coronal loops. You should also be able to identify, or at least talk about, the classifications or characterizations of the CMEs based on based on maybe their speed, based on intensity, based on association. Are there other structures you can see like prominences or like flares associated with the CMEs you're seeing on the image of the sun for that day? You should be able to go through an image of the sun and describe all the structures you're seeing. So let's just play around with these. I would want each of you to tell me at least three structures you're seeing on this image. So three structures you can see on this image of the sun. So I would want to see it in the chart. So give me three structures you can see, at least three. Yeah, I can see at least three of them. So you should be able to, show me or state three features you can see from this image of the sun. So I'm looking at the chart. Sunspot. Can you really see sunspot there? CME. Uh, can you see CMEs there? Somebody said flares. Can you see flares there? Uh, okay. Nishaya said CMEs. Osman said flares. I said three, so try to give me three. So Nahum said corona holes, CME, solar flares. Okay, we'll see those who are right at the end. Osman said sunspot. Okay, we'll see. Sushmita said loops, solar flare. Okay. Nishaya again said solar corona holes. Okay. Uh, Wisdom said S-class solar flares. How did you know it's S-class? All right. So corona holes and corona loops. Okay. Uh, Setting. I hope I'm pronouncing that name correctly. Setting said Setting can see flares, CMEs, corona loop, hole. Okay. Sheyi can see holes, flares, and you did not complete it. Okay. Mohammed can see solar flares. Prominence. Can you see prominence? Ah, yeah. Oh, that's okay. Let's see. Corona hole, I think. Okay, you think. All right. I'm also thinking. So, Rajamahat, Rajamahanti can see flares, corona holes. Okay, Ahmad can see solar flares, corona holes, prominence. All right. So, Wilberforce can see sunspots, CME, solar flare. Okay. Radiamante. Okay, you're adding prominences. Okay. Okay, Nishaya is saying, how do we draw the distinction between coronal holes and sunspots? Good question. Okay, I'll answer that question when we get to Q&A. Remind me of that. So Osman, Ahmed, flare, sunspot, prominence. Okay, Eyitayo, sunspots. Okay, CMEs and coronal holes. Prominences, according to Susmita. Okay, Anusha said coronal holes, solar flare, CME prominence, and then Samsuluga holes, flares, UV light, the spectrum. Okay. Okay. Anusha said, I am still not clear. Okay, about prominence and coronal loops. Okay, good, good. That's a good question. All right, I'll answer that. So La Mesa said sunspot, okay, flares, okay, prominence, okay. Adioye said CMEs, solar flares, sunspot, okay, good. Okay, Osman, that dark region is corona hole. And the sunspots here are not dark, rather bright. Hmm. Okay, Osman Ahmed. All right, good responses. Okay, so uh okay, okay, let's try to respond to those questions I saw here. So I think the first question I saw here is how do we draw distinction between coronal holes and sunspots? Beautiful. Now, if we go back, if we go back to what I said when I was talking about sunspot, you will observe that the location of sunspot, remember, is usually within the equatorial region of the sun, usually close to the sun's equator. Let's go back to that. So let's let me show you. Yeah. So observe the location of occurrence of sunspot, usually around the equator, between plus and minus 30 degrees of the sun's equator. So you usually get the sunspot within the sun's equator. Now, when you see that dark spot within the equator, it's very likely to be a sunspot. Now, when it comes to the sizes, the coronal hole is usually very covering a very large portion of the sun compared to compared to sunspot. For example, Aha, take a look at this. Take a look at this image here. If you can see this image, these dark spots you're seeing, they are all sunspots. They are all sunspots. But if you see a coronal hole will cover a larger region compared to the region covered by a sunspot. So that's why it's called a hole. A sunspot is just a spot, relatively, a spot, as you can see. But a coronal hole is large that it can cover up to uh, 1/10 of the sun. But a sunspot cannot cover 1/10 of the sun. No. But a coronal hole can cover 1/10 of the sun. A coronal hole can cover large portion on the surface of on the corona of the sun. So take note of these differences. One, location. Most times a sunspot is located around the equatorial region of the sun, while a coronal hole can be observed around the equatorial region as well as around the polar regions of the sun. For example, if you take a look at this, hold on, I'm coming. Let me show you guys this. All right. So when you take a look at this image, you observe that the coronal hole can be seen around the equatorial region as well as around the polar region. But sunspots are usually restricted within this region. So I want you to know that and know those are two main differences when it comes to um, coronal hole and sunspot. Very good question. And then how do we draw distinction between coronal holes and sunspots? Okay, I've answered that. The location as well as the sizes. I'm still not clear about prominences and coronal loops. Beautiful. So prominences are filamentous. So let me see if I can show you that prominences again. Uh, these are good questions, and I really want you guys to know those differences because I also had those challenges if I got to graduate school. I also had some confusion surrounding that. So it's good you ask those questions and you know them now. Uh, you won't believe I can't find where is the image of that prominence? I, I thought I showed. Aha. Okay. So this is a prominence. Now take a look at this prominence and then let me see if I can share two screen at the same time. Okay, this is one here. Uh, let me see if I can open that again and share. I'm trying to place both of them side by side. So hold on a minute, please. Okay, it seems that will be a problem, but then okay, let me share the images and see if that would make some sense. All right, so let me stop sharing this and then let me share my windows. Mm, I'm not able to share both images, but okay, I know what to do. Hold on. All right. Okay, can you all see these images now? So I believe you can see this image I'm sharing, right? So when you take a look at both images, what you have here what you have here is the prominence, and what you have here are coronal lobes. Now, observe that in the prominence, okay, let me call them, you can see that it's sketchy, it's rough. It's not as smooth as what you have here. So what you have here are filamentous, emissions, ejections. You can see, and usually most times associated with open magnetic field lines too. But what you have here, you can see they are closed magnetic field lines. You can see you don't really have emissions per se. It may be associated with emissions, but a lot of times they are not emitted. They are just suspended around the corona, and then with some time they dissipate. But what you have here, in many cases, they are ejected. In many cases, they are ejected. And coronal loop, I think another difference is uh, in the lifespan. I can't recall exactly, but I think coronal loops can can be in this can be here for a very long period of time. But prominences, I think they are short-lived because with time, they either eject particles or collapse back towards the surface of the sun. So, but from these images, you can see the differences clearly. This is filamentous, and this is fine, smooth, relatively smooth, fine, compared to what you have on the prominences. So as you keep looking at these images with time, you get to know to identify each of them and be correct while identifying them. So I can't recall the lifespan, but I think one difference is in the lifespan. I can't recall now, but when I recall that, I'll send it to you guys, and it's something you can also read up. So that is the difference you can see in the structure. Structurally, they are very different. Their lifespan is also different. The nature of the magnetic field, you can see here you have the magnetic field clearly suspended, but this magnetic field is open and ready to eject particles. So these are some of the differences I can remember in my head right now. So the next question is saying the dark region is coronal hole and the sunspots here are not dark. So how did you know the sunspots if they are not dark? Rather bright regions. Bright, really? Sunspots are not really bright. They are cool. They are cool dark regions. So maybe what you're seeing are not sunspot, but maybe small solar flares, maybe C class solar flares, or even B or A class solar flares. So what's the difference between sunspot and AR? What do you mean by AR, Raja Mahanti? AR, AR. What do you mean by AR? I can't recall what that abbreviation stands for. Maybe you clarify. How solar flares and solar activities are observed, both ground-based and space-based. Oh, ground-based, of course, right from time they've always had a lot of telescopes and ground-based observatories. So you can observe the sun with different instruments from the ground. So there are so many observatories used that are able to use telescopes to watch the star. I was in the telescope in an observatory in one of the universities in Brazil. That's Univapi, yeah, University of Paraíba. So they have a telescope there, and that evening we're able to see some stars. No, were we able to see stars? Yeah, of course, we're able to see stars, but mostly the moon. I was able to use my phone, to capture the surface of the moon. You see the craters and all that on the moon. Very interesting. So while in space, you have a lot of instruments. You have the Solar Dynamics Observatory. You have the Solar and Heliophysics Observatory. That's SOHO. You have SDO. You have SOHO. And I also talked about Parker Solar Probe. That's the PSP, which was just launched in 2018. And you also have GOES. Yeah, GOES. That's another you can use to observe all of these things. So if you would want to go into heliophysics, these are interesting instruments you may want to know about. Focus on one of them, learn more about them, and sorry. So focus on one of them, learn more about them, and you should be able to apply for positions, opportunities, and all that for PhD and stuff like that. So and suggest any recommended simulations, data set, or study materials like NASA resources to understand this field better. Oh, this would be cool. That's Sam Suluga. Okay, send a DM to me. You can send a DM to me, and you can also, or you can send an email, whichever one you prefer. I think you're on the WhatsApp group, Samsu. Yeah, I think you are. Yeah. So the speed of CMEs come from polar hole and equatorial. Can we say about their speed? Polar holes. What do you mean by polar holes? Do you mean coronal holes? Yeah, if you're talking about coronal holes, yeah, the speed of solar winds can come from coronal holes. Yes, because the particles are living. How can I? Okay, can you imagine a string holding a set of beads, and hanging, maybe you're hanging the beads on the two sides, maybe to your ceiling, right? Okay, let me see if I have my board here. Let me try to see if I have my board, and then I should be able to. All right, so assuming this is a string, you 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 hang to your ceiling. This is it here. So let's extend this here, and let's extend this here. Yeah, you can see how beautiful my drawing is. And on this string you have beads. You have beads, right? You have beads. So many beads, you know, attached attached to this you know, to this string. So many beads, attached to this string. All right. And these beads, remember, they are all on the string and they are hanging on your ceiling. This is your ceiling here. And these are the beads, on the string. I want you to imagine what happens. I want you to imagine what happens if you break or cut this string here. What will happen to these beads? You agree with me that they will all fall off, right? These beads will all fall off. So you have something like this. You have this part of the bead. So all these beads will fall off, and all of these beads will fall off, right? And remember, they will be falling off with a very high speed under gravity, right? So this is the same thing that happens. This same thing that happens on the sun. So you have these magnetic field lines, and you have the particles, oscillating and drifting and carrying out some kind of motion on the magnetic field lines. So what happens when you break that, when you what happens when you a kind of split that string, that magnetic field line? The beads, the particles will fall off suddenly. That is what happens in the sun too. So what happens is that those particles leave suddenly with very high speed, and by so doing, they fasten or increase the speed of already existing solar wind. And the kind of solar wind we have in this case is what we call fast solar wind. So the speed of CMEs or of solar wind, not maybe CMEs, probably CMEs, but the speed of solar wind particles can be fastened by coronal holes. Yes, that's that. It seems everybody is drawing on this board. So let me stop. Let me close the whiteboard. Everybody seems to be drawing on this board. You are collaborating on this whiteboard. No, I'm not. Hold on, I'm coming. I want to close the whiteboard, but I'm not able to close. Why? Okay, stop. Sorry, I'm trying to exit the whiteboard. Hold on a minute. Why can't I exit this whiteboard? uh, all right. So I'm trying to exit the whiteboard, but I'm not able. I don't know why. All right, so let me go back. I think I've been able to do that. Which window? Okay, so I'm coming. I'm trying to. Okay, so the speed of. Okay, so the next question is what's the difference between ionospheric storm and geomagnetic storm? Okay, we'll be talking about these, but ionospheric storm simply uh, it has to do with changes in the maybe in the density or plasma concentration or ion concentration of the ionosphere, and usually occurs within the ionosphere. But geomagnetic storms are usually as a result of the impact of maybe coronal mass ejections or solar flares or interplanetary magnetic field. The interaction between interplanetary magnetic field and Earth's geomagnetic field. So that causes some kind of storm, especially if the interplanetary magnetic field is pointed southward, right? So it causes geomagnetic storm. We are going to talk more about this in subsequent lectures, but ionospheric storm has to do with mostly increase in the density of the ionosphere. We all know the ionosphere has to do with, of course, ions and electrons, they are plasma. So when you have sudden increases in the concentration or density of these ions and electrons, you have an ionospheric storm. But geomagnetic storm, when you have a sudden change in Earth's geomagnetic field, then you have a geomagnetic storm. And what causes this geomagnetic storm? An ionospheric storm. Hold on, we'll talk about that in subsequent sessions, a step at a time. So active region, I don't, AR, active region. Okay, active region has to do with sunspot. Yeah, okay. But when we talk about active region, we're talking about regions from which some of these structures can emerge. When I mean structures, I mean CMAs, prominences, solar flares, and so on. Those regions of active dynamics, active magnetic, connection and reconnection. Those are active regions. So the sunspot is also an active region. Take note. Wherever you have CMEs emanating from, those are all active regions. Wherever you have prominences and other structures emanating from, those are active regions. So sunspot is also a type of an active region. And all of these structures we are talking about, they are all, you know, uh, they are all uh, types or parts of active regions. However, heliophysicists usually consider regions from which coronal mass ejections and solar flares and prominences are emanating as active regions. So sunspot region is also a very active region because most times you have coronal mass ejections emanating from that part. So if you have coronal mass ejection emanating from a sunspot region, then that's an active region. But if you have no coronal mass ejection emanating or you have nothing going on there, that's just a region not active because nothing is going on, right? That's just a plain summary of what an active region is. So a sunspot can be an active region, but not all active regions are sunspots. That's what I'm trying to say. Shei said, does it mean that there is always holes and loops on the sun since the magnetic field are either closed or open? Always. Wow, good question. Wow, good question. Yeah, now it depends. When we say open magnetic field lines causes coronal holes. No, one open magnetic field line cannot cause a coronal hole. No, one cannot. No, but billions and billions of them, when you have so many of them being open, then you can have massive ejection of particles. And then you can have depletions from a certain part of the corona. When you have this large depletion, then you have a corona hole. But when you have just open magnetic field line from just a small region, and no, those are not holes, right? They are not holes. Yeah. And then you said sun magnet. Yeah, so it's only a hole when it is massive, when it is large, when it covers a large portion of the sun, then it's a hole. If it's just a small region, it's not a hole. It's just maybe a small depletion, not a hole, not categorized as a hole. And loops on the sun, you also always have loops. Yeah, you always have loops. That's true. Yeah, you always have loops, and those are coronal loops. Yes, coronal lobes are always present on the surface of the sun. Very always, almost always. That's if the sun is active and we have uh, high solar activity and low solar activity. When you have high solar activity, you have more of these loops, more of these holes, and so on. And just a small question in the slide, having the content of the coronal hole as we see the majority of them being present near the poles of the sun. Is it because of the magnitude of the magnetic field? To be honest, I don't have the answer to this question. This is a good question, Nisha, but I don't have this question. Maybe you should send it to me in as a message. I think this is a very, very good question. I've never thought about this. Nishaya. Okay. Great question. The whiteboard is still loading. Okay for me. All right. That's Sam's. Sam's are sunspots truly empty? No, nobody said sunspots are empty. Who said that? Nobody said sunspots are empty. They are not empty, by the way. They are just region. They are just cooler regions, relatively cooler regions compared to other, surrounding regions. And they are dark, not they are dark in the sense that they are dark. No, they are dark in the sense that their temperature is different from the temperature of the surrounding region. So they are not empty. No part of the sun is empty. Not even the coronal holes are empty. No, they are not empty. Rather, the coronal holes are depleted. Please take note. I did not say empty, I said depleted. So depleted means compared to other regions of the sun, that region of the sun is having a lower density, a lower number of particles compared to other parts. So it's never empty. How can a part of the sun be empty, my friend? That's not possible, right? So it's not empty. So what is the physical process that caused the solar cycle to vary in strength from one cycle to another? Oh, beautiful. Good question. And I think that has to do with the dynamics of the sun. You know, so the sun's dynamics are not stable, it varies. So, and that's what scientists are still observing up to now. However, the driver of all of these has to do with the sorry, excuse me, has to do with the magnetic fields, the nature of the magnetic field, the connection and reconnection and disconnection of the magnetic field. These are these are the factors that define how the solar cycle will vary. So these are things that are still being observed. There is no particular answer to this question as at today. So it's something you can decide to go and research for your PhD. If you've not done your PhD, you can say you want to know what is actually driving this variation we observe. Scientists for now know that there is a variation. What causes variation? Magnetic field variations, dynamics too. But what exactly causes that? I doubt if anybody knows. But then you can also find out. That's a PhD question, I tell you. If you can actually answer it for your PhD, you can go for your PhD. So, as of today, are we in high solar cycle? Yeah, high. So, yeah, as of today, we are in high. Yes, high. Yes, high. So, uh, high solar activity part of the solar cycle. High, not low. So why do some CMEs travel faster than others? Beautiful. Where they are sourced from? Yes, what actually causes the CMEs, remember, it has to do with the entanglement of magnetic field lines. So when magnetic field lines entangle and entangles themselves, at some point they break, and when they break up or disconnect per se, what happens is that they release this massive amount of sorry, they release this massive amount of particles. What happened? Okay, I hope nothing happened. Okay, they release this massive amount of particles, and that causes this variation. Again, other activities like solar flares, like maybe the presence of prominences or coronal holes and so on, can cause the speed to vary. So it's a good question. It's one that we can have conversation about later. That's a very deep question. Yeah. So what varies them? The sunspot, the activity happening in the sunspot. Do you have solar flares? Do you have prominences? So if these activities are occurring simultaneously, like we observe sometimes, of course, the speed will vary, right? So how do these localized magnetic field lines, magnetic field interact with one another? Man, too many questions. Sure, I will drop the question. Okay. Thank you, sir, for taking your time to explain to clear our doubts. Okay, okay, sounds all right, fine, thank you. So, I think how do these, okay, this last question, how do these localized magnetic fields interact with one another that extended in the corona? Is it due to interactions we see in coronal mass ejections and flare? No, no, no. It is actually the interaction between magnetic field lines that causes the variations we observe in CMEs and flares and so on, right? So it's variation magnetic field, dynamics that causes the variations we observe in CMEs and flares and not the other way around. I don't know if that's what you're trying to ask. If I'm not clarifying you, you can message me and I will respond to that question if that's not what you mean. And how they interact. I don't know if you've heard about connection and reconnection of magnetic field lines, not just on the surface of the sun, also in our magnetosphere, which you'll be learning about in the next session. So uh, I think with this, we should be ending today's session. If you have any other question, you can DM me and we can talk more. So I wanted to share one last thing with you guys, and that is okay, that's the solar energetic particles. So this is one last thing I wanted to share with you guys, solar energetic particles. So I will share this with you guys and you guys can read it up. It's not very complicated, and that's it. So like I said, you can always trace everything you see in space weather back to the sun. That's why it's important for us to talk about the sun as much as we can. And I think this is the last time we may be talking about the sun, except maybe via DMs, or you have questions you can ask, or during the project and so on. So thank you for attending this session. I'll be sharing the link to the oh, you know that my laptop has not been charging. I never knew. That's fine. All right. So I think that's it for today. So you can DM me if you have any other question, right? Yeah, about installations, DM me. We'll talk about that. I'll direct you to how we'll do that. All right. Have a good weekend. Goodbye, everybody.